All right, so hi, I'm Effie. My Twitter handle's here. That's because that's where the slides will go at the end of this talk. So if you're seeing something and you're like, I need to write this down super quickly, you really don't. Just wait, it'll be there. And today I want to talk to you about working with AOSP, what it's like, and based on my experience. I work at a Berlin startup called Lotti, and we build custom tablets for kids. And I want to start by going over the main takeaways of this talk. And the first one is that while AOSP is like a big scary word, with some extra tricks and extra hacks, we can actually really use everything we know about building apps and just build the apps for AOSP. And we can even use the tools we know like Android Studio. AOSP does have a few extra tools that were meant to really just help manage a large code base. We're going to go over them, but to name one, a tool called Repo allows us to perform bulk operations on lots of Git repos at once. Another major takeaway is that AOSP is, in fact, open source. It means that it's all there. If you are looking for how did Google write this, or why did they write this, or where is it in their AOSP code base, it's all there. You can read the code, you can understand the code, you can read their commit messages, you can read their history, you can read everything you need to know about AOSP. Which also means that the AOSP code search is a really useful tool that will be super helpful to you. So let's start by talking a little bit high level how Android operating system is structured. And the Android operating system, I bet maybe you've seen all the layer sketches at some point. Lots and lots of layers, but by and large, it's split into two sections. The top section is what we call AOSP, is all the things that are open source, we can use them, we can change them, we can customize them, we can look at them. All the bottom part of this picture is very hardware-specific code, so it includes special drivers and other customizations to maybe the kernel, and things that every manufacturer does themselves, and they package it, usually in the forms of like large blobs, and build AOSP on top of it. Many manufacturers also change AOSP themselves, so they fork AOSP and change it, but overall, by large, the top part is where it's easy to make changes, it's where a Google developer will spend most of their lives, and the bottom part is where a Samsung engineer would spend a lot of their time. When building AOSP, or when building the operating system, we're generally building a few separate images that are containers for specific logic. So, for instance, we're going to build a system image, which is mainly the Android framework, which is mainly AOSP. We're going to be seeing the boot image, which is where the kernel, the RAM disk, lives. We're going to see the vendor image, which is all the proprietary drivers and things that are specific to that specific vendor. We're going to see OEM image, which is where the carrier-related configuration and customization live. There's a bunch more images. I thought these were just the more important ones. So say I am not working at Samsung, and I want to still customize AOSP. What can I build for just out of the box? The first and easiest answer is the emulator. For the emulator, we don't need any of the hardware stuff because it's all emulated. We can build for the emulator by just pulling AOSP code and just using it as is. We can create AVDs, we can do a bunch of stuff that will end up resulting in this beautiful, beautiful AOSP build. You'll notice that it's very stripped because, of course, Google Play services and all the other apps that are proprietary don't exist on the basic AOSP. If I wanted to go and build, for instance, for the Pixel, I would need all these drivers and all these, we call them for short BSPs. I would need to build AOSP with them. Now, if I'm building for a Google device, Google actually released all of them for us. So we can go to this website, download the binaries. For example, in the case of a Pixel, they will be for the Pixel 3 and for Qualcomm chips. We'll deploy them as blobs into our AOSP tree and build with it. If we wanted to build for other devices, the support there is pretty limited. Samsung, for example, I'm mentioning them a lot, but they haven't officially released all their drivers. An alternate route we can take is we can use Lineage OS. And Lineage is an Android-based and AOSP-based operating system, and they incorporate all the major versions of AOSP into their code base, and they support a larger array of devices, either by finding some drivers here and there or that kind of stuff. Another thing about them is that many of these devices that you find on their list are older. That's actually pretty nice, because if you have a device that cannot be upgraded for, say, Android 12, there is a chance that Lineage supports that, and you will be able to get a lot of the features of Android 12 by upgrading to Lineage. So if we look at this picture again, only slightly differently, when we want to customize AOSP, we're mostly talking about the first two layers. We're talking about the OEM apps, if we wanted to change the launcher or the setting app, and we're talking about the framework itself. And we're not really talking a lot about the vendor implementations and the kernels. So what would be some examples of changes that we can make? Very easy to think about. We can add, replace, customize the system apps. Say we wanted to completely replace the launcher with our own custom launcher, or we wanted to create our own setting app. We can do that. Say we wanted to create a magic app that can access restricted APIs, or even if we saw APIs that are not available at all to anyone and we wanted to access those, by building a system app, we can access those APIs. Another change that's fairly straightforward to make is if we ever wanted to change the status bar, the nav bar appearances. And if we are very ambitious, we can change how the framework itself reacts. So if we decided that we want to display our own custom animation when we switch between apps, the frameworks would be the place to do it. So before I go and start diving a little bit deeper into the tools we need and the tools that AOSP uses, I want to also give this preface that AOSP is literally just regular code. It's written in Java, it's written in C, C++, it's just a lot of it. It's more than 1,000 Git repositories. They are Git though, so we can use Git the way we know it. It is more than 100 gigabytes of source code, and when it compiles, it can turn into 250 gigabytes of compiled and source code. It's just a lot of it. So, what tools do I need to get started with writing my own AOSP code? The first thing we need is a Linux machine. No other operating system is supported. However, I put the Windows WSL signal here. It is possible to build on WSL. It is, however, not possible to run the emulator from WSL. I did try that, actually, and I even tried running the emulator on my Windows side and connecting to it through ADB from the WSL side. I had some fun there, but no. Really, if we wanted to run the emulator, we have to take the images over to the Windows side, but then we cannot debug them very easily. It's probably best to have a dedicated Linux machine. The other thing we need is we need the machine to be pretty strong. From my initial attempts with WSL, it took me about 7 hours to build the full build of AOSP, and say 2 hours, 3 hours for incremental builds. So the system is pretty smart about that, and it can tell when little changes have been made and kind of build only those portions, but that's still a long time. And especially when starting up, we're going to be building AOSP quite a bit, because we're going to make all these dumb mistakes of building the wrong configuration and all these little changes that we'll need to make. And waiting 7 hours is a little bit too much. So what we ended up doing is we ended up just getting a dedicated server. I posted a link here for Al's post about how to configure, how to find out the perfect setting or the best setting for a build machine. And there are some hacks about if you want to really buy a server and kind of host it yourself. We just found that to be way simpler. And on this particular configuration and with these settings, our builds were really fast, which was super nice. This is, by the way, even faster than what Google says. They say their builds are 40 minutes. So we shaved 10 minutes off of that. If you're using a server, the thing that would probably be useful for you is to have a desktop access to it. You can do a lot through the command line, but of course you cannot, again, open the emulator or the IDE through a command line. So my choice of stack here was to use No Machine to create virtual desktop for my server. And to top it all, I use Tailscale. Tailscale is a VPN that flattens out your network and basically means that you connect any computer you want to it, they will all appear as if they were in your local network. The setup for Tailscale is super easy and straightforward. Really, I am really loving this tool. It really made my life super simple. I don't have to deal with security issues, which port am I connecting in, none of that. It's all pretending to be on my very local network, super easy. Now, if we're working and we're changing AOSP, there will come a point where we are making some changes that we want to save locally and not necessarily commit back to Google. Then we really kind of have to start copying and having our own repository source. Now, you can get by storing some of the changes or some of the repositories in one place and then continuing to fetch all of the others from Google. We chose, because we thought this could just get a little confusing, because if we get a certain version from Google and a certain version from our own servers and try and build them together, they'll fail. We'll be in a world of like, what's coming from where? So in order to make a full image of AOSP, a full mirror of AOSP, we decided to use GitLab. GitHub is really awful for this job. It's just the repositories are too big and it will take forever. And GitLab has two amazing features that actually make this way easier. One of them is that it has groups. So the AOSP Git tree is a tree. It has branches and groups. So having a structure that supports that is pretty awesome. And the other thing is that it has a tool to import the manifest, literally import all these 1,000 repositories at once, instead of just going one by one and hitting clone, clone, clone. This is amazing. It wasn't completely seamless, but it was way better than trying to one by one copying that. I want to talk a little bit about the tools that AOSP itself is using. The first one we already kind of mentioned, it's called Repo. Repo is a Git aggregator. It's a Python program that uses Git to provide functionality similar to what is provided by Git submodels. So instead of, again, trying to Git clone one by one repositories, we want to be able to clone all of them, or sync all of them, or commit to all of them. Git is our repo is our friend here. The first command that usually people do is called git repo init, which we give a URL to, and then we get back this beautiful XML file that is a list of GitHub repos, of Git repos. And the second command that we'll use is repo sync, which will go over this manifest file or other manifest. It can be 2 manifest, 3 manifest file. It will aggregate all of them and just get us all these repositories. The second useful command that we'll use a lot is the environment setup script. The environment setup script will activate a bunch of useful commands that we'll use throughout building and playing around with AOSP. And one of the commands that exists in this script is called launch. And launch is how to configure the build. So we can build for lots and lots of AOSP targets and lots of configurations. And the launch menu is literally asking us, which configuration do we want to build AOSP for? And then after we picked it, it will display this amazing property list of this is what we picked. And in this case, is platform version 12. The build target is a custom emulator target that we created. The build variant is user debug, which means that all the debug ports are open and we can debug and we can connect into our AOSP build. The architecture is 8664, so it will work on Linux and Windows. And then we're ready to make. We're ready to build AOSP. The build system for Android is sort of in transition. Android MK is the older version of the build system, and they are sort of in the middle of transitioning to Sung, which is Android BP. Both of these, the first thing that will happen, they are sprinkled throughout the tree. The first thing that will happen when we build is the build system will go over the tree, pull out all these Android MK and Android BP files, make a giant list of, okay, I need to build all these different things from every folder, from everywhere these exist, and then it will start building them. So this is how the very initial flow of starting to build or building our first AOSP build would look like. We would repo init with the URL that we want to pull the manifest from, and then we will repo sync, which will actually sync all the repositories. We will activate our environment script. We will launch with the whatever target we want to build for, and then we will hit make. This parameter -j is a hint to make how many cores to use to make it a little bit faster. Another really useful tool is called AID gen command. It configures Android Studio or IntelliJ project files with the relevant module dependencies resolved. So we want to change something in the framework. We don't want to really go and start opening Notepad or whatever and starting to change these files. We want to have a full IDE. We want to be able to navigate to source or find the usages of a certain thing or search for a certain file or class. And we want to just have our IDE set up for us. And this command will do it. It will launch the IDE for a specific subproject or a build target or a specific folder. And it will configure the coding styles and all these IntelliSense stuff that we love and use. And after using that, what we'll mostly see is something like that. Just IntelliJ with some folder. This is the AOSP setting up. Some of it is still not configured correctly. There's a bunch of tweaks to do, but the core essence of it is that now you can work as you are used to, and the only thing you still have to do is make and run the build through the command line. This is, I want to say, very similar to what a Google developer in the Android framework team life would look like. So let's talk about development. If we said that we can easily change and make modifications to these top two rows, the framework stuff and the apps. For the framework stuff, again, we're here. This is how our framework, this is how we'll change the framework, this is how we'll build it. We're gonna go and we'll build it with Make, and we're gonna use all the tools that Android provides, and we're gonna use IntelliJ or Android Studio, probably on our Linux, which is why I also screenshotted the whole no machine window setup, because it's not very possible, or it's not very feasible to keep switching to our own dev computer or to our own dev environment, be it Windows or Mac, for this purpose. But if we want to build apps, then we just want to build apps. And this is very similar, or literally identical, to what we're doing in our day-to-day lives. We have an emulator with the app that we are changing. We have maybe a custom build flavor for AOSP, and when we hit play, we can take our APK, we can build it with Gradle, we can do everything we already know how to do, and deploy it onto this custom image. So how do we do that? And I added these 5 amazing steps to getting from the Linux to our own dev machine. Step 1, we want to take our APK, our Gradle built app, and put it in the AOSP build. The second thing we want to do is we'll want to create an emulator image with this custom AOSP build that we just did. We want to also sign the app with the same platform key, or the same key that AOSP signed it with, also on our Android Studio side. And then we can deploy locally. We can just hit play and override the APK with whatever changes that we were just making locally on our machine. Profit. The other advantage to this approach, by the way, is that we can use all the imports, all the libraries, we can use Maven, and we can just completely use even stuff that wasn't really incorporated in the framework. So if we're writing our apps, for instance, with Compose, and the system apps are not written with Compose, this was not yet integrated into AOSP, but because we're using the dependency that we're used to, we can just do that. So let's go over these steps and see a little bit what they mean. Step 1, we take our app and put it in the AOSP tree. And we can see here the app APK with an amazing name. And we add to it the Android BP. We add to it the file that gives instructions to the make system how to treat this APK, what to do with it. So how did we get here? How did we get to having this structure? Again, an amazing plan of 3 steps. We need to create this Android BP for our APK. We need to add a link in the manifest file to our own repositories, because now we want to have something brought in from a different source. And we want to build AOSP with our APK. So the Android BP in this case is super straightforward. It says, okay, here's my APK, this is how I want to call it. Sign it with this awesome certificate, because now I want to be cool and I want to be part of the platform. And give it some privileges, because again, if we're cool, might as well be cool. Now, we don't want to normally add to them or change the original manifest file, because then we have to keep track of it and keep merging differences if there are. But because repo can aggregate different manifests, we can create a different manifest that will point to our other repo with the APK and the blueprint. And we can just say, hey, put this in this path in vendor Lottie, put my APK, my blueprint, everything that I need. And we can add this manifest to the list of manifests that repo will look for when it's creating its big list of repositories to pull from. Now, if we have all this in place, we can just hit make, and it will be built with our APK, signed as platform, embedded into the AOSP. So, step 1, embed our app in the AOSP build. Check. Step 2, now we want to create an emulator image because we want to use this emulator image to develop locally on our machine. So for that, we want to create a zip file with all the emulator images. We want to take this zip file and put it in our own SDK location on our own computer, be it a Mac computer or a Windows computer. We need to add this properties XML file for Android Studio to be able to construct the list of different emulators that you can build from. You just need a file for that because that's what Android Studio is looking for in order to parse us this list. And then we can create an AVD with our custom image. I know, it's lots of steps. Creating a zip file with the emulator image. Officially, the command is make SDK repo. I don't know why, but this isn't working. What is working is make emulator image zip. And this will result in this long file, system images and your username zip. Okay, so we have the zip file with the emulator images built on our server. Now we take it, we copy it over. In this example, it's a Mac. It can work really on your dev machine, whatever it is. And we extract it into the SDK location for Android Studio to search for. So in this case, I created the Android 33 branch, and in it I extracted the content of the zip file. All right, so we have a zip file with the emulator images. We put it in our SDK. Now, if we open Android Studio will not see those images. It will not be able to tell us, hey, build an AVD with this. Why? Because it needs a special properties XML that it parses when it starts to create those lists of images that we have on our computer. Just literally copy it, which is what I did. I just literally copy it from, I don't know, Android 32 or whatever other images you already have. And I changed a bunch of properties here. I don't know, Lottie, the Lottie images, whatever you need to change to just so you know when you see it on the list that it's not a cookie cutter image, it's whatever you made. All right, it's getting better and better. Now we can open Android Studio. We will see it on the list with the properties that we changed. And now we can create emulator images, emulator instances from it. All right, making progress. We got the app embedded in the AOSP build, and we have an emulator image. Now, if we run this emulator image and try to deploy our app, we made some changes, we try to deploy our app to this emulator image, the first message we're going to see is the package with the same name already exists, but it has a different signature. Why? Because if we go back in time a little bit, we signed it with the platform key. And Android Studio signs it with the debug key, or if, I don't know, if you have a specific configuration, it signed it with a different key. So now we have to take this platform key and import it back to our JKS file, to our JKS key store. Now, I'm not going to go over this because it's really just boring. It's just follow these commands in this gist and you'll have it. The platform keys, or the keys that are that the AOSP signs by default, are testing keys. So when you're ready to release, you'll need to create release keys for AOSP, but the testing keys are fine for debugging purposes, development, etc. And then you just add a signing config to your Gradle file, and magic. And now we have also sign your app with platform key working. We are already technically at step 4. Now when we hit play, whatever changes we made locally to our app will be deployed to the image and replace whatever app we were working on. Profit. Are we profiting though? Because the next thing you'll try and want to do is you'll try and use APIs that are probably not accessible to the public. So this is code that I copied directly from somewhere where I saw, okay, this is how you set your phone in airplane mode. But as you can see, user handle all is red. It's not recognized at all. It's like it's never there. It is never there, literally. Because when I go to the AOSP codebase and I open this file, I see that this user handle all is annotated by system API, which means that for the final stages of using the SDK, it's literally being stripped away. It's not there. The annotation processor takes this and takes this property and just removes it completely. But wait a minute. I can use here, look, it says system API, vendor. I should be able to use these APIs. I don't need to resort to tricks that we all know, like Anyway. So, the reason for that is that the SDK we compile against doesn't know we can access these APIs. It doesn't have any, the SDK itself has been already stripped of these system APIs. And that's why our build fails. So we want to trick it. We want to create a custom SDK without the annotations to compile against. And then when we take our APK, our compiled APK, it will work even against the stripped version because we'll be in the system at that point. And for that, we're going to use this clever trick where we're going to take, because the annotation process happens after the initial compilation, it's a two-stage compilation. First, compiles the code as is, then the annotation processor goes and strips all these APIs away. We are going to just take the class before it was stripped. And it does exist because the AOSP build system saves all the intermediate steps that it took, and this helps consecutive builds be faster. So with some zip magic, we can take the intermediate state, put it in our final result, copy it over to our dev computer, and compile against that. So here's where you can find those intermediate build results. And with some zip magic, we're gonna create the Android jar with all the things that were stripped away from us. We take this Android jar, we copy it over to our dev computer. We tell our dev computer to build against this special magic SDK, and magic, it's all there, as if it never happened. Last but not least, I want to say something about searching AOSP codebase. The entire AOSP codebase is searchable through cs.android.com. And this is the most useful tool ever, because what you get back is a really, really good, even with some IntelliSense results. You can go to source, find usages, you can see the history of commits. It's really awesome. And whenever you're like, hey, I don't know, what is this? Why was this made? How was this made? This is your answer. It's really super convenient and fast. And with that, that's it. Thank you so much.